All right, guys, we'll get started real quick. I don't want to wait too long because chances are we're going to lose people before we get more people. So hi everybody whoever has not met me before, my name is Ethan. I'm the project's exec. But for most of the project tonight, I'm not actually going to be running things. I'm going to turn it over to some of my lovely committee members. And go ahead, if you're a committee member, just give a wave in the chat or one of those little yes or no icons, I suppose. All right, thumbs up from Jack. So yeah, we have a few people here that aren't they're not just regular students. They've been working with me to build this workshop and to prototype it and everything. But for the rest of you, I kind of want to go around the room because there are some new faces. I know Brady and Brady and Dan, I have not really talked to yet or interacted with other than today. Everybody else, I think I have met before and talked to before. So we'll start with projects members. So Will, if you want to go ahead and go first, go ahead and introduce yourself and give us one of your hobbies.
I'm Will. I am a sophomore. I guess one of my hobbies right now is playing guitar.
Sweet. All right, Muchin, I'm throwing it to you next.
Hi everyone, my name is Muchen. I'm a senior in electrical engineering. My hobby, stargazing, I would say.
Sweet. Okay, Jackie, you next.
All right. Hi, everyone. I'm Jackie. I'm currently a sophomore majoring in electrical engineering, and one of my hobbies is playing soccer.
All right, Jack.
I'm a hello. I am a junior. Wow, my brain's not working tonight. I'm a junior in electrical engineering, and one of my hobbies I can't do right now, unfortunately, is rock climbing.
Nice. All right, Nishay.
I'm Nishay or Nish for short. I'm a junior in computer science, and one of my hobbies include reading.
Solid. Always a good hobby. And then Khan, why don't you wrap it up for the committee?
Hey everybody, my name's Khan. I'm a senior in electrical engineering. One of my hobbies is playing tennis.
Nice. And then for some of our non-committee members, we'll go around. Brady, you want to start it off?
Hi everyone, my name is Brady. I'm a freshman, want to be an electrical engineer major, and one of my hobbies is spike ball.
Nice. Are you undecided?
No, I'm not. Like my major is electrical, but like technically I'm not electrical.
Oh yeah, you're still in your pre-major
Yeah.
stuff. Nice. All right, Antonio.
I'm Antonio. I'm a sophomore in EE. I'm actually the communications chair of IEEE, and I really like riding bikes.
Nice. And you want to take the next one?
I mean, I'm already unmuted, so I can go.
No, let's do Dan. Let's do Dan. Come on, let him take it.
Hello, I'm Dan. I'm a super senior, so it only took me 4 years, but I finally showed up to something. And I guess my hobby would be, I also like riding bikes. So
Sweet. All right, Ethan, you could be next after you just took a big spoonful.
Yeah, right as I take a bite. I'm Ethan. I'm field ops exec. I would say that probably one of my hobbies would be cooking, as you can see. And I guess lifting and running, I like to do that every other day. I kind of bounce back and forth between I'll lift one day, run the next day. I also like snowboarding. Used to snowboard competitively, so yeah.
All right, Cole and Amelia, you two are last. Who wants to take it?
Doesn't matter to me.
All right, Amelia, go for it.
Okay. Hi, I'm Amelia. I'm a junior in studying electrical engineering. I'm also the Thon chair for IEEE. Some of my hobbies, I guess, I play soccer. I'm on the Penn State club soccer team as well. And I play racquetball whenever they decide to open up the gyms here. But I enjoy playing some racquetball too.
Nice. All right, Cole, take us home.
My name's Cole. I'm a sophomore with my intended major is computer engineering. And one of my hobbies is skiing. I'm on the club ski racing team here.
Nice. We got a bunch of athletes. Cool. So I guess I'll finish up by introducing myself. So I'm a senior in electrical engineering, and like I said, I'm the projects exec. So I do this all the time. Kind of what you're going to be doing tonight has been my nightmare for the past week, and it's been the projects committee's nightmare for the past week. But I'd say a couple of my hobbies include doing this kind of maker stuff, and then I also love video games. Just got into Among Us recently, and that's been my new addiction. So if any of you want to hit me up, like, let's go. I'll kill you on the spot. So yeah, if you guys ever want to contact me outside of the projects, experience here, you're more than welcome to. I can help you with personal projects. If you need help picking out parts or getting parts, I'm always here. So I'm more than available for just workshops. All of the exec and to some extent the chairs, though not to the same extent as us. We're all available for your resource. So if you need to reach out to us for class help, picking professors for classes, we have all been, we've been through the ropes. We've made it through this far, so we have a pretty extensive knowledge combined, about what college is and what the EECS department is. So without further ado, I'm going to share my screen and I'm going to pass it over to Will to start us off tonight. So let me grab that for you. And I will share my screen here in just a sec. Come on, there we go. Back. And all right, can you guys see my screen?
Nope.
No.
No?
There we go.
There we go. All right, Will, it's
All
all
right.
you.
So welcome you guys to workshop number 2. If you have any questions, don't hesitate to ask. Yeah, let's go. So what is Arduino? Arduino is a hardware and software company that designs a variety of development boards and controllers. They're best known for their AVR-based boards, such as the Arduino Uno, Nano, Mega. They make a whole bunch of development boards. The AVR series of microcontrollers was developed by Atmel in the late 90s, but it's a cheap and compact microcontroller solution, and it's really useful in a lot of different electronics projects. AVR chips on their own can be really difficult for beginners to program and interface with, but Arduino boards make it really easy to work with them. The Arduino project is open source, so you might see companies other than Arduino making some of your boards. You might see that Arduino did not make the board that we gave you, but they're all part of the same family. They all do the same thing. At the bottom of I'm going to see if I can annotate here. No, I guess I can't. That's fine. At the bottom right of your screen, you can see this is an example of one of the more common AVR chips called the Atmega 328. If you look on your Arduino board, you can see that there's one of those on there. This is the same AVR chip that is used with the Arduino Uno. So next slide. So let's take a look at the board. You can see a picture of the Arduino Uno here. It's the same kind we gave you. If you look at the top line of pins up there on this picture, these are the digital pins. So they can be used to send or receive high or low signals. Like, for example, you can receive a high signal from a button press, or maybe send a high signal to turn on an LED. If you look at the bottom right of this picture, you can see A0, A1, all that. Those are the analog pins. Those are used to measure like a specific voltage coming from an incoming signal. And we're going to learn a little bit more about that later. But we'll keep going for now. The Arduino can also communicate with other devices using the built-in serial monitor. So for example, the Arduino could take in some data from like a temperature sensor and then send it back to a computer connected via the USB port. And we're going to see an example of this in a couple of slides. So yeah. So when it comes to programming your Arduino, if any of you are familiar with C++, it uses C++ syntax. There are two main things that you need whenever you make a Arduino script, or they're called sketches. So you need a setup function, which you can see kind of up on the top part of the code snippet over there. The setup function is run once, and it's used primarily for telling the Arduino what we're going to be doing with the different pins that we're using for our project, or maybe starting a serial connection with a connected computer. We'll see that in the next slide. And then the other thing you need is a loop function. Down you can see at the bottom of the snippet. And the loop function contains the set of instructions that you want the Arduino to run forever. So when the Arduino runs the sketch, it'll run the setup once and only once, and then it will run the loop function over and over and over again. So we're actually going to see what exactly this code snippet does. So if I can share my screen.
Let me stop sharing mine, and I'm
Okay.
going to give control over to Will for a sec.
Thank you. Bear with me here. See if I can make this work. Okay. So if you guys want to pull up your Arduino IDEs that you guys downloaded, let me know when everyone has that up with a thumbs up. Okay, I see Cole. Okay. Well, once you have it open, if you go to File, Examples, Basics, and then Blink, you open that up, you're going to get this example Arduino sketch. You do not need to plug anything into your Arduino. All you're going to need to do is you are going to need to take that cable that we gave you and then your Arduino and plug it right into your computer. Go ahead and give me a thumbs up when you all have done that. Okay, great.
Where'd you go to get that example? It was File, Example.
File, Examples, Basics, and then Blink.
Gotcha, thanks.
Yep, no problem. I'll give it a second.
So I think for most people, this will pull up a new window.
Yeah.
Don't worry about having to save this. Will's going to walk you through kind of how to get it onto your chip there in a sec.
Yeah. Okay, so this is the same code snippet that we saw before. I'm going to make my window a little bit smaller so you guys can read it a little bit better. Can you guys see that okay? Okay. So first, we're going to take a look at the setup function I was talking about. This is going to run once, and we're going to use that to tell the Arduino that we're going to use the built-in LED as an output. If we had an LED, for example, hooked up to, I don't know, like pin 13 or something, what we could do is instead of LED built in, we could say 13. And that tells the Arduino that we're using pin 13 as an output, and we can use it to send higher lit signals. And we'll see an example of that a little bit later. But for now, we're going to keep it at LED built in. And then output here just tells the Arduino we're going to use it as an output. If we were going to use it as an input, we just change it to input. Oops, input. But we're going to keep it at output. We're not going to change that part. So now the loop function. This is going to run forever. We're going to start off by giving the Arduino a digital write statement. What digital write does is it changes the state of a digital pin that we would have defined in the setup function up here. So we're going to tell the Arduino, okay, that built-in LED that we told you was an output up in the setup function, we're going to set that to be high. And that's going to turn on the built-in LED. And we're going to tell the Arduino delay 1000, and delay pauses the execution of our sketch for a certain amount of milliseconds. 1000 milliseconds is just going to be a second. And then we're going to tell the Arduino, okay, now make LED built-in low, which is going to make the LED, built-in LED turn off, and then we're going to wait another second. Now, once we get to the bottom here, since this is the loop function, we're going to go right back up to the top and do the whole thing over again. So as long as the Arduino is plugged in, it will keep on doing this loop function. So if you guys all have your Arduinos plugged in, I don't know if you can see this, plugged into your computer. If you click this, if you go up to Tools, make sure that your board is set to Arduino Uno. And then make sure that you have something here for port. It may not be COM6, but just make sure you have something clicked there. It should automatically figure it out. Okay. Is everyone doing okay? Is everyone making through it smoothly? Okay. Once you have that figured out, if you click this upload button, you'll see it will compile the sketch down at the bottom, and then it will upload it to your Arduino. And you should see, I don't know if you can see this right here, the built-in LED is turning on and off every second. So you can see, Ethan might be able to give you a better look.
Mine's blinking faster than yours should be. Mine's blinking at twice the speed, but it's kind of what it should look like.
Yeah.
Sorry, I was playing around with the code.
No, you're good. So is there anyone who's having trouble getting it onto their Arduino? Or are we all doing good? Okay. Well, if no one's having any trouble, then I'm going to go ahead and hand it off to Jack to tell us a little bit more about analog to digital conversion.
All right, so Ethan, do you want to share your screen again?
Yep.
All right.
Let's go ahead and go back to that.
All right, perfect. So analog versus digital, this just gives sort of an overview for those of you that don't know. So analog data is data that exists as a continuous signal, which is usually denoted by a sine wave, which you can see there down on the left in the little picture there. And that represents physical measurements. So our world that we live in is analog, which just means that information and data are constantly flowing and changing. Data isn't turned off, things can be turned off, but it's constantly, it's not strained to two values as is the case with digital. Analog also represents, like I said, more detailed and refined information which humans can read. So it's easier for us, since we live in an analog world, to sort of, interpret this data. But analog is very susceptible to noise, which just means interference. So things like bad signals can cause interference, or multiple signals near each other, things like that can cause interference. It also tends to have a lower signal quality than equivalent digital signals. Now, digital, on the other hand, is what exists in like computers and modern smartphones, things like that. And that is only, that's only in binary, which is like ones and zeros. When Will was talking about high and low, that's the same thing, on and off, that sort of stuff. And that's denoted by a square wave. So this just means that these signals are non-continuous and time separated. And it's extremely easy for computers, like I had mentioned, to read and analyze this type of data. Digital represents discrete numbers, usually 1 and 0 in binary, but not always, to represent information. Digital signals are less susceptible to noise because there's only two states which they're represented in, and they generally have better quality signals as well. Now, Ethan, if you want to click to show the clocks, just as an example.
Yeah, so actually, before we get to that, are there any questions about the analog versus digital disparity? And you guys don't have to raise your hands or anything. You can just go ahead and talk. Are there any questions so far? All right, I'm seeing shaking of heads. So yeah, I'll go ahead and pass back over to Jack.
So here we just have like these on the left. There are those really dated clocks that I mean, Old Main has them, but other than that, you really don't see analog clocks much anymore. We're mostly in the digital world with digital clocks, which are there on the right. So that's just an easy example to sort of put it into your mind and, conceptualize this, especially since we're virtual right now. Okay, so what is ADC and how does it work? So ADC is just an abbreviation for analog to digital converter or conversion, whichever you want to call it. And it converts varying analog voltages into digital signals so that they can be more easily read by digital devices. And this allows us to collect information from real world instruments and then analyze it digitally with computers. Now in an Arduino, the ADC in a 10-bit 5-volt Arduino, which is what we're using, it uses the analog voltage to charge an internal capacitor, and then it measures the time it takes to discharge that charge on the capacitor across an internal resistor. And the Arduino monitors the number of clock cycles, predetermined clock cycles that pass before the capacitor is completely discharged. And this number of clock cycles is what's returned by the Arduino in the form of a binary number. And this technique is referred to as successive approximation, since it takes several clock cycles to accurately approximate the input voltage. Now here I have an equation, and I'll just go over really briefly. On the left side, we have the 1023, that just is 2 to the power of 10. That's how many bits, because we're in 10-bit for these Arduinos. The 5 is just the 5-volt voltage that powers the Arduino. The ADC reading is sort of our expected output, and then the analog voltage measured would be our analog voltage that's going in that we want to convert to digital. So yeah, are there any questions about that? I know I kind of went a little fast, so if anybody has any questions or if there's any confusions, please don't hesitate to ask. Are we good? Okay, then I'm going to hand it back off to Will.
Actually, but before we do that, I'm gonna kind of interject here.
Okay.
So one of the things about this whole analog process, as Jack said, it takes a couple of clock cycles. So your Arduino, think of it as like a computer. It does many calculations and many operations per second. Not nearly as much as, say, like a laptop or a desktop computer. It's not even close. But there's been this struggle for years about how scientists and engineers can get like almost real-time analog readings, because for so many of these analog digital converters, they use that same process that Jack had talked about. So now scientists and engineers and stuff can get this down to like nanoseconds, which is actually really impressive. But if you think about capacitors, it takes them time to charge up and time to discharge. So there are other issues like what kind of capacitors you use. So this isn't quite as simple as we've put it here. There's obviously more digging. So if this is interesting to you, I would recommend researching it. There's a lot. You will get lost down the rabbit hole pretty quick. But just for tonight, all you need to know is that the Arduino is actually approximating these voltages. It can get only so close with the number of bits that it has. So Jack said you have 10 bits. So it's 2 to the 10th power. Or really that's 1024, but also 0 is a value. So it's like 1024 minus 1. I know this is kind of harkening back to some EE2, or not EE270, Compeng 270 stuff. And some people may have not even taken that yet. So yeah. Any questions before we turn it over to Will? Nothing, man. You guys are quiet tonight. Trying to get your money's worth, I suppose, huh? Sweet. Also, welcome, Avery. I saw you.
What's up?
Avery's another one of our exec. So maybe if there's time towards the end, we'll let him do the icebreaker like everybody else had to do. So, all right, I'm going to turn it back over to Will here.
So I'm going to do a quick little demonstration with this circuit here. I'm going to share in the chat a link to the code I'm going to be using. There's a GitHub link in the chat now. You can feel free to follow along, but I'm going to be sharing my screen and using Tinkercad. And I'll show you that in just a minute. Okay, so you should be able to see Tinkercad now. So Tinkercad is this really great online free piece of software you can use where you can simulate an Arduino and a breadboard. And it's really useful for prototyping. And we're going to use it to take some data from this dial and turn it into a percentage that it's going to read out on the serial monitor. So a potentiometer is basically just a resistor whose value changes depending on the position of the dial. So for example, if the dial is all the way over here, resistance is full. Dial all the way here, it's a very, very low resistance, whatever you want to do with it. So it has 3 terminals here. The first and third terminal you connect up to ground and your power source. And then the middle terminal is going to be the output, as if it was a resistor. So for example, if we have this hooked up to analog pin 0 over here, it will get 5 volts if it's here and it's very low resistance, and it will get 0 volts if it's all the way down here with high resistance. And we're going to use that. So I'm going to take a look at the code over here. So we're going to set a couple of values right here. ADC max, this is just going to be the maximum value that we know that our inbuilt ADC can handle. It'll be, as Ethan said, it's 10 to the 10 minus 1, 1023. And we're going to define pole. Pole is just going to be a value we're going to use later to set how often we're going to check the value of that potentiometer. So we're going to do our setup functions. They're going to run just once, and we're not actually going to define any pins. We're not going to tell the Arduino what pins we're using because we do not need to do that if we're using analog pins. We only need to do that for the digital pins up here. Analog pins, we don't need to do that. So we're going to start a serial monitor connection here. We're going to do that by typing in capital S, so serial.begin 9600. I don't want to get into what the whole 9600 thing is, but basically, it's the baud rate. It's just the, it syncs up the connection between your Arduino and your computer. So serial.begin 9600. So now we're going to go on to our loop function. I'm going to make this a little easier for me to see because Zoom is kind of blocking out my view here. Okay, so let me pull it up for myself here. Bear with me. Does anybody have any questions while I pull this up? No? Okay. Okay. Sorry about that. So the first thing we're going to do is if we want to get the value that we have plugged in from the potentiometer that's on analog pin 0, we can use analog read. What analog read will do is it will use the inbuilt ADC at whatever pin we put in here and return a value from 0 to the maximum ADC value, which we know is 1023. So if we just print this right now, if we want to print something to a serial monitor, we can do serial.println and then whatever we want to print. If we just print this right now and we run it, and we open up the serial monitor, you can see it's giving out some value here. It changes from very close to 0 to very close to 1023, depending on where we check it. So that's what analog read does.
Now, we'll give you guys a couple of seconds here to make sure everything's plugged in. So one of the things that you might have an issue with, and I would recommend using another wire or some small screwdriver for, like this, is the potentiometer, because they are so small, and these were the only ones I was able to get. Sometimes you can get these ones that are nice and have a little knob on them, but unfortunately the IEEE stockroom was out of those. So is anybody going to have an issue turning that little knob? I've gotten it with a pencil or a pen before, but if you have a little screwdriver or something sharp, like a pair of scissors, you might be able to get it with that. Does everybody need to take another look at the code, or are you guys just looking at the circuit now?
Could you go back to the code real quick?
Yep. You guys don't need to worry about this line for now. We're going to be changing that in a second. The only line I've added from the GitHub link I sent is this line right here, I believe. Okay, is anyone still putting it together? It looks like, okay, it looks like most of us are ready to go. So we don't just want to output the analog read value. We want to be able to do something with this analog read value. We want to turn and do a percent. So Arduino lets us use this really neat function called map. And what map is going to do is take in a value, take in the bounds of an input range. I'll show what this means in a second, and then bounds of an output range. So if we give the map function a range that we know the input is going to be, for example, 0 to 100, 0 to 50, or 0 to 1023, and we give it another range, which we want to convert the value into, like 0 to 100, it will scale the value based on the range that you give it and the output range that you give it. So it's kind of weird to understand. If anybody's confused by it, I don't blame you. I probably didn't explain it best as anyone else could. But we're going to, hopefully you guys can understand a little bit better by implementing it in this code here. So it takes 5 arguments. It's going to take the input, the lower bound of the input, the higher bound of the input, and then the low and high bounds of what you want it to be on the output. So we're going to start by doing input. Our input is going to be analog read with A0. Oops, A0. So this is going to be our value that we get off of the potentiometer from analog pin 0. Okay. We know that analog read from A0 is going to be somewhere from 0 to 1023. So from 0 to the maximum value that the inbuilt ADC can handle. Yeah. And then we know we want it to be scaled from somewhere from 0 to 100 if we want a percent. So for example, while you guys type that out, if we got analog read A0 and we saw that analog read was getting 512. 512 is half of what our upper bound is. So we would output half of what our upper bound is for our output. So if it got 512 in here, since it's halfway in between 0 and 1023, it would output halfway in between 0 and 100, which is 50. If we got something around like 775-ish as the analog read here, we would get something around 75 here. All the map function does takes in an input value. You give it a range that you know it's going to be in, and then it outputs an equivalent value for a different range. So does everyone have that down? Any questions about that? Okay. So now that we have analog read as a percent value, we are going to assign that to a variable, and we're just going to call it percent. So in percent equals our map function. So now percent, whenever it loop hits this, percent is going to be updated to be whatever we get off of the potentiometer. So now let's do something with that percent value. We're going to print something to the serial. So serial.print line. And we're going to do percent. So this is just going to print our percent value to the serial. That's pretty straightforward. And then we're going to delay. If we just let this go, I actually want to show you what this would do if we just let this go. If we just ran it as is, it kind of goes crazy. If you can see at the bottom, it kind of updates really, really fast. And that's not necessarily useful to us. So we want to slow it down a little bit. We're going to do delay poll. And poll is this this thing we defined up here. But when it hits this, it's going to do delay of pull, which is 1,000, so it's going to delay 1 second every time it runs the loop.
And just to jump in real quick, Will.
Yeah.
So that pull value that Will set that you see up there is actually in milliseconds. So say our application or whatever application you're designing this for only needs to be read once a second. Well, that's 1,000 milliseconds. So that's what we're going to be using for this. But if you want it to read faster, you can make it read a lot faster. It's actually, it's pretty scalable. So if we were to go to like 500, say, and we have to change that value up at the top like Will's doing right now. So that's going to read twice a second. So you're more than welcome to experiment with that, but by default, it's just going to read once a second, according to the code that he had sent you. But if you look on screen, he said you can change it to 500, 100, whatever value. Yeah, you can have it read, once a day or whatever you want to set it to. But yeah, just wanted to throw that out there.
So is there any reason why you're pound defining these?
Yes. So I guess we could technically do something like this, like int poll, equals 1,000 or whatever. But that kind of isn't super efficient because that means we're defining it every time it runs the for loop, and it's just not very good. We can't define it. We cannot define it in setup because it is local. It would be local to void setup here. So we define it outside of both of them. A quick note about define. Define is a little different than just setting like a normal variable. What define does is when it compiles, it actually substitutes in whatever value you have here. So when it's time to compile this code, it won't try to get the value of whatever it has saved for poll. It will literally just replace poll with whatever value you defined up there. So that's a quick note about design.
Is there a difference between defining like outside of the loops and doing like int percent if you did it outside of the loop or int poll outside of the loop?
You mean like if we did something like this?
Yeah. Well, just like creating poll. Like if you said int poll equals 1,000 up at the top instead of saying define poll 1,000, is that any different?
I don't think so. We can try it out. That should work fine.
I just don't know like if it's stored differently.
Yeah. So the difference between doing define poll and int poll is that when you do int poll, the value 1,000 is associated with poll in the Arduino's memory. If you do define like we had before, oh my gosh, what is that? Whatever. If you do poll like we had before, it would not store poll in the Arduino's memory. It would literally just substitute out wherever it sees poll in the code for the value of that.
I gotcha.
So think of it as when you're defining a variable, the only time that poll name is going to be used is when the developer or when the designer is referencing that value. What Will is trying to say is the Arduino, when it gets the code, when the code is uploaded to it, it will never see that poll name. It will just see that 1,000 value. So that's more for if you're just designing and you want to be memory efficient, because if you define that, it's only defining the integer. You don't have to define also like the name and then link them together. So in memory, the int poll, whatever, is going to take up about twice as much for something like that. Now, if it's a super big value and you have a ton of memory to work with, probably doesn't matter in the long run. But for small stuff like this, or say if you were developing 20, 30 years ago, that would make a whole lot of difference. So yeah. Also, real quick, Brady, you had to go at this point, right? Okay, so here's what I'm doing. I just want to hold things for just a sec. We're still recording, so if you need to get off to your exam, go ahead and do that. Get your pencils ready. Make sure you have your ID, whatever you need to do. Grab a drink of water. We wish you the best of luck. Also, If anybody ever has an exam around the time of a workshop, come for as long as you feel, and then you're more than welcome to dip out early. But I knew that Brady had let me know ahead of time. So I'm just gonna be posting this to like YouTube or something afterwards, or maybe we'll have it up on the IEEE site. But yeah, so you're good to go. Just wanted to call it out.
All right, thanks guys, appreciate it.
Does someone else have a question?
No, I was just gonna say, on the topic of the whole pound define versus defining an integer outside of like at the top there. I think another thing with that is that like you can apply some logic to it, so it's like in the scope of any function that you would write, you could apply logic to it and potentially change it. But the pound define is essentially treated as like a constant.
Yeah.
Okay.
If you're using, I was always told that if you are, if you have like a setting that isn't going to be changed by the code, like a value that isn't going to be changed by the code, it's generally best to use pound define at the top. Okay, so this should be ready to run, so let's give it a shot. You guys can upload it to your Arduinos if you have the circuit hooked up. And in order to get to the serial monitor, let me just show you how you would do that. If you have, just opening up the IDE again. If you have your IDE up, you can get to the serial monitor by going to Tools and then Serial Monitor. Well, I don't have my Arduino connected, but another window would pop up with the serial monitor. So let's see what happens if we run this. I'm going to go ahead and run it on Tinkercad here. So you can see it's reading out 0 every second, but if we change potentiometer value here, it'll go all the way up to 99. Or if we do somewhere, let's go right halfway. It'll be around 50. It's not exactly 50, but yeah, there you go. So is anyone having trouble getting that to work, or does anyone have any questions before I hand it off to Ethan? Okay, great. Thank you.
Sweet. So everybody got that working, huh? Everybody who at least has an Arduino in front of them and their circuit. So we're actually going to build upon the topics that both Will and Jack have presented so far, and we're going to take that to kind of a new level here. So everybody has their circuit in front of them. It should look something similar to, let me go ahead and switch, something similar to this right here. And I'm going to actually move this camera down. Sorry for the motion sickness associated with this. All right, there we go. That looks pretty good. Let's pull this out. All right, so everybody can see my circuit, right?
Yes.
Fantastic. All right. So a couple things that we're going to be looking at are how to get the serial from this into something with a little bit more of a real world application. Not that I'm saying a serial connection isn't real world application, but most of the time you're going to be using that value to control some other stuff. Say, you know, maybe you want to turn on lights, or a great example is like a thermostat. So now a lot of thermostats are going to be digital. So they're going to take a value, and you know, once it's hit a certain analog voltage threshold, because most likely the thermistor in there is going to be outputting an analog voltage, it's going to want to click on something, and that's going to be done using digital logic. So what I'm going to do right now is I'm going to flash up on the screen a circuit that I'm going to want you guys to build, but it's going to have to be built a little bit differently. Some of you may not have enough wires for the one that's in this picture, but let me go ahead and see if I can pull this up here. Let's go to present, share screen. There we go. So you guys should be able to see this circuit, right?
Yeah, we see it.
Yes.
Nice. So whenever you're building this, I know it might seem like you don't have enough wires. You can ignore the wires on the right-hand side of the breadboard. Also, can you guys see my mouse or no?
Yeah, I can see it.
Okay, cool. Makes it easier to point stuff out. So these wires on the side, you don't have those. Don't need to worry about them too much. So you already have the potentiometer connected right here. So you have one wire going to ground, one wire going to your positive 5 volts, and then they're going to be coming out of their associated pins down here. So whenever you're going to be building this circuit, and so this middle LED here, actually, it can go in any order you feel like, but we've given you 2 green LEDs, 2 yellow, and 1 red. So the way that I'm going to be building mine is going to be 1 green LED, or sorry, 1 red LED all the way left, and then 2 yellow LEDs to the right of that, and the 2 green LEDs are going to be to the far right. And instead of that little black wire, you're going to have these 330 ohm resistors. It's going to be the orange-brown resistors, by the way. And those long orange wires are going to be most convenient for you to run from the digital pins, which in this case, it's 9 through 13. We're actually going to be using 8 through 12. So I'll give you a couple minutes to put that together. Also, in my camera, can you still see my hands? Yeah, okay.
Yeah.
Yep.
Sweet. So while you're building this, I'll go over a little bit of the analog to digital and a few more practical applications. So a lot of audio applications. So some of you may be audio enthusiasts or just music enthusiasts in general. So a lot of the circuitry that goes into that is not only analog to digital conversion, but digital to analog. So you'll hear those as DACs, digital to analog converters. And so typically if you have a nicer DAC in your phone or whatever device you're listening on, typically you'll get better sound quality. So now like a lot of sports cars and stuff have, super advanced DAC technology, blah, blah, blah. Pretty much it's all the same. It's all made overseas and imported, so it's cheap. But if you get like a really, really nice audio setup or something that you'd plug into, say your computer, typically that's how you're going to get better audio out of your computer. Also, would any of you be interested if we did kind of like an amplifier workshop in the future? Kind of talking about that stuff a little bit more. Just trying to gauge interest.
Yeah, absolutely.
Yeah, that'd be cool.
That's cool, man.
Sweet. Yeah, some of you, if you were with the club last year, you may have heard about us wanting to do a Bluetooth speaker workshop. Unfortunately, it fell apart when we were all sent home. But I still think that'd be something super cool to do, even if we're just doing kind of the amplifier part of it, the speaker part of it. And hopefully that'd be a take-home project. So we'd have a nice PCB. You guys can have it all bundled up. Go ahead, show your parents. Or show your friends. I don't know. My parents don't care about that shit, so they're like, it's all technology. It's all black magic, which is okay. I guess they don't need to understand it. So has anybody finished building this circuit yet? Take that as a resounding no. guess if I'm still building, there's a good chance everybody else is too.
What did you do as the order for your LEDs again?
It may be flipped. I honestly forget, but at least in the demo, which I don't know if you can see me holding this up in my camera, but the demo I had, well, I guess it's supposed to look like that. I don't know, it might be inverted for you, but I had my red one all the way left, my two yellow in the middle, my two green all the way right.
So like red on 8, and then from there.
What's that?
I said like red on 8, and then go from there.
Yes, that's what I have.
Okay.
Again, these things change whenever we are, whenever we're prototyping and stuff. Speaking of prototyping, I also want to mention that there were others behind the design of this workshop other than just Will and Jack. We also had Nish, who was helping out with code, and I've got Khan. He's kind of my right-hand man for logistics. And then Muchin and Jackie are two of our newest members. So they weren't too involved in this workshop, but hopefully in future workshops we can get them doing some stuff. Anybody else finished up yet?
Yeah.
Couple of head nods. All right. Some of our veterans here. This sucks. I wish I could see more people at one time. Oh, I can. Here we go. All right. Now I can see all your beautiful faces. If you need me to, I can make this view bigger. Is anybody having problems seeing it? Okay. Any questions so far on the circuit or any of the topics that we've covered tonight? Take that as a no as well. Well, I'm glad we're all professionals with this. So the career fair, I'm sure they're hiring. So we have some sophomores in here that apparently can get jobs. I think Brady was the only one that was a freshman, so maybe he might not have gotten a job, but everybody understands digital to analog conversion, or analog to digital. My goodness, sorry, misspoke. All right, everybody ready to move on to the coding part? All right, getting a lot of head nods. Sweet. So I'm gonna stop sharing for just a second here. Also, does everybody have kind of like a little drill bit or something? Ooh, move this back. Come on, focus. Yeah, I just have a little screwdriver. You can use a pen. You can use, yeah, I was gonna say, if you have a MyDAC, there's a really, really good chance you have, yep, I see 2 or 3 people with those. Okay. Mine is buried somewhere in all my stuff, but I just got this little thing from a driver kit. So go ahead and throw that in there. All right. Let me go ahead and pull up the code window. So I'm going to be sharing another link with you that's going to be kind of the skeleton for this potentiometer to LED display that we have. Let me go ahead and share that. So the most recent link, GitHub link, is from me. All right, everybody good to move on? All you have to do is copy and paste that code, and if it's taking you a little bit longer, just go ahead and shout out, be like, hey, stop, slow down. I know that I've done this a lot, but that does not mean that anybody else has. So if I go fast, you'll have to excuse me. I'm just excited. All right, I'm gonna be sharing this little window right here. I might move around a little bit. So let's go ahead and take a look at this. So we were using the initialize and define, and I know that was a question from before. In this code, we are going to initialize them up here. Because this is an array, you probably can define it, but for our sake, we're just going to initialize it like this. So it's just an array of integers. That should already be in your code. What is not in your code is down here, this void loop and everything. And you may want to start a new file for this. I'm not exactly sure what your setup is on your computer, but I just opened a new file. It's going to be very similar to what we've done with the last code. So if you're building off of that, that's perfectly fine. Will, in the meantime, would you mind go ahead and sharing the completed code for the first circuit, just so it's in there? Thank you. So this is just for future reference for if you're watching the recording back. Anyway, we're going to continue using this. So underneath map, go ahead and do another line here. I'm just going to tab over, move my junk out of the way here. So we're going to be doing a lot of the same for the as the last example code. So we're going to have to do an int, so integer, and we're going to call this one LED. And this is going to be very similar. We're going to be using that same map function. So remember, in the map function, we're going to need first our value that we're going to be inputting, analog read instead of analog read. A0 is going to be the pin. And then next, we are going to be using the lowest value of what we're inputting into the map. So again, that's 0. And then also the highest value that we're going to be inputting, which is 1023. And this is actually going to be a little bit different. Instead of going to 1 to 100, you see we have 5 LED pins. So we're going to be going 0 to 5 for our map. This 1023, I also just realized, is going to be our ADC max value that we put at the beginning. So you can leave that as 1023, or you can just have the ADC max. Everybody have that so far? Head nods all around. Sounds good. So we have that. Now, what are we going to do with it? Well, we can see that we have 5 LEDs, but we also want a state for the LEDs to all be off. So you can see here, 0 is going to be no LEDs on, 5 is going to be all LEDs on. And down here in this for loop, we can see that we have some stuff to find. I won't exactly explain this right now. I'm going to leave it a little bit up in the air, a little bit magic. If you want to go in depth with this a little bit or research it on your own, I encourage you to do so. You guys have these kits for another week. And there's plenty of time for you to monkey around with it. If you don't already have an Arduino, I would very highly recommend an Arduino Uno as your beginner board. So if you want to go ahead and explore this, but the general gist is we're starting out with an initial value of 0. And then that value, depending on kind of what the mapping is, we're going to be mapping of these LED pins that we've already established. We're just going to be increasing those based on the map. And that's down here in this if statement. Will, did I explain that correctly? You're the one who wrote this code. You and
yeah, I'll just go over it again real quick.
Go over it real quick.
If you're not familiar with for loop, it just It's kind of like the loop function in Arduino, but it does it a certain number of times. What this for loop is basically saying is we're going to start with some variable I equals 0, and then while I is less than the number of pins we have set up for LEDs, so the number of LEDs we have, we are going to increment I by 1. So basically what this is going to do is for each LED, it's going to check if it should be on or off. I don't know if that was...
No, that's excellent, because I had completely missed this increment I at the end. That's why I said I'm kind of going to leave this a little bit black magic for you guys. So when we're going through, we're actually going and checking each LED incrementally. So it's going to loop through, and each loop of this is going to check only one LED. So knowing that, let's go ahead and get into our first little bit here. It's 3 tabs in, if you're wondering how I'm getting to that point. So if it's bigger than the I value, so if it's at a certain value or above whenever it's looping through, or just in general, if the LED should be on, meaning if the value of this mapping equates to one of the LEDs, we're going to go ahead and turn it on. So this is actually we've used analog read. I'm going to introduce you to digital write. And so this outputs a digital signal, which we've learned already is just going to be a 1 high or 5 volts, however you want to refer to it as, or a low or 0 volts. So when we're doing this, we're going to be digital writing, and then whichever LED of the LED pins should be on. And we're going to add some brackets here because the brackets, it's going to be using that I value that we've established before, and it's going to be enabling that LED. Again, I might not be explaining this exactly how it should be explained, but just know when it cycles through, it's going to see, okay, if an LED should be on, we're going to turn it on. So that's going to be how we turn it on. Any idea how we're going to get it off down here?
Just write low.
Yeah, so we're going to be writing it low, which is just 0 volts. We're not supplying it to anything. So we're going to go ahead and copy that, paste it down here, and then instead of high, we're going to have low. So that's a pretty easy fix. All in all, this code is pretty short, and it's going to be doing a lot more than what most code is going to be doing at this length. I'm going to give you guys a couple of seconds to copy that down.
I have a question, actually.
Yeah, what's your question?
Can you explain why would we divide size of the array of LED pins that we have initialized up here by the size of the first item of that list?
Yeah,
so
so
go ahead and take that.
that is a product of the C family of programming languages being really iffy. If any of you have taken CompSci 131 or 132 and you're familiar with Python, this is basically how you do dot length. This is how you get the length of an array. Or not dot length, whatever it is for Python. Basically what we're doing here is we're taking the size in memory of the array LED pins that we declared up at the top and dividing it by the first element of LED pins will give us the total number of actual items in the array. Yeah, that we're just doing this because C doesn't have a built-in way to get the size of the length of a list like that. Does that answer your question?
It does, yeah. So just to clarify, so size of returns the size of its input in bytes or in bits? Or?
Yeah, if I understand it correctly, that's right. So it would get like, let's say LED pins is 64 bytes or something like that. This is how I understand it, at least. LED pins is 64 bytes, and each item in LED pins is 8 bytes. So size of LED pins would give 64. Size of LED pins of 0 would give 8.
Is it
So,
bytes or bits?
Man, I don't know. I'm gonna be honest, but I just know it's just the size in memory, and all of the elements in that array have the same size. So when you divide the size of one element by the size of the whole, you will get the number of elements. Sorry,
Yeah,
I don't know the specifics.
No,
of size
that makes sense. It doesn't matter if it's bytes or bits because it's still the same calculation. It's just
yeah, I'm not quite sure.
I'm just wondering for
question.
like future projects because I've never.
Let me look that up for you.
So the one thing I can interject here is whenever we're working in the Arduino IDE, it's really user-friendly. It converts everything for us, which is a blessing and a curse because memory management is horrible. We don't really deal with memory management all that much. So if we were to put in like a number, if we were just to put in an integer, it's going to save that in whatever format it can think of first. And whenever I say whenever it can think of, there's obviously an algorithm behind it. But for just general using numbers, unless you explicitly say binary or decimal, there's a good chance it's going to convert between them, no problem. And that's just a result of this programming language. It's actually a modification of C++, which is pretty common for these microcontrollers, even the not Arduino ones. So if you have to ask whether it's, decimal, binary, hexadecimal, stuff like that, chances it's all three at the same time, and it's not really determined until the Arduino or the program finds a use for that value.
Ethan, I can confirm that size of returns size in bytes.
Bytes?
Sorry about that. Yeah.
Okay.
Sorry about that.
Gotcha. Makes sense.
Yeah, but if you want to do math with it, the IDE is going to know, okay, you need a certain type of that variable. It's going to convert between them, unless you explicitly say I want to do byte-wise division or bit-wise division. So, kind of a long-winded answer. Thank you, Will, for clarifying that. Anyway,
yeah, hopefully that was that. I can't talk to Dave. What the heck? Sorry about that.
Yeah. Anyway, you're not going to have to worry about it until you get to some lower level programming or upper level courses, I should say. Anyway, there's one more function that we need to write in on here, and it's something that we've already used. Is just the delay. We don't want this running constantly, so we're going to type in the delay function. And you can see up top, our poll this time is only 1 millisecond. This is going to be running real fast, but remember we have to cycle through all of the LEDs very quickly. So if we want to avoid flashing or blinking, for example, we have to really limit this down. So if you were to set it for a second, it would take a really long time for all of these LEDs to update, and they're going to update sequentially. But we want them to go faster than we can perceive. So think of this as going just, as fast as your computer screen updates, essentially. But anyway, after we've done this, we're going to go ahead and upload it. Actually, I just want to make sure that I am on the right. So Arduino Uno, and then COM5. So I have that already up. But yeah, we're going to upload this. It may ask if you want to save. So I'm just going to save mine as September 17th, A, or whatever it is. You can save it for, oh, forgot. My bad. I've been working with Python too much. You need a semicolon after the delay poll. Some of you may have caught that already. But you're welcome to save it however you'd like. Let me go ahead and just... All right. So you may or may not be able to see. Let me go ahead and turn off a couple of my lights, actually. You may or may not be able to see that there are actually only 4 LEDs on. And I've maxed this thing out. Yeah, I'm zoomed in all the way. I've maxed this thing out. So another issue with these Arduino analog to digital converters is that they're pretty inaccurate, all things considered. 10 bytes is not a lot. So we're going to have to trim down some values here. And a good way to see that is actually taking a cue from an earlier part of this workshop. So real quick, in this void setup, we're going to go ahead and begin a serial monitor, or just a general serial connection. Go ahead and type that in. And then down here in the loop, just right before we declare that int and we do the mapping, we're going to go ahead and do serial dot print line. And all we're going to do is just print out this analog read. Oh, and we got to do this on A0. Make sure to put a semicolon at the end of that line. And then go ahead and upload your code again. Should be pretty quick. Another way to get to your serial monitor, by the way, is this little icon up here in the upper right-hand corner. You see that? It might be really small. If you go ahead and click that, it'll bring up the serial monitor. Can you guys see my serial monitor right now, by the way?
No.
No, you can't? All right, let me see if I can switch the screen. Here we go. Yeah, this should be updating very rapidly for you guys. So my potentiometer right now is maxed out. And you see how it only goes up to about 905? About the average value. Does anybody have a different value than about 905? So we're around 910-ish.
Mine's going to like 10, 20-ish.
Okay. So it means you've got a good potentiometer. I unfortunately did not. So I'm going to have to go back into the code and trim that a little bit, trim these values. Is anybody else having an issue where it's not going all the way to 1023, 1020-ish? Okay. So congrats to me for picking out the dumb potentiometer. Let me go ahead and go back to the code here. So you guys seeing my code now? All right. So this is going to happen whenever you're going to be prototyping, testing, building stuff out on breadboards. It's just not going to be very accurate. And that's just a result of the quick and dirty nature of a breadboard. So what I'm going to do is I'm going to trim this ADC max down by, let's just say 100. You guys might not need to trim it that much. My old code, I only needed to trim it by about 25. And that's using a different potentiometer. So I'm going to go ahead and upload this now. And we should see, hopefully, if I have this correct. All right. Unfortunately, it's not cooperating. I may need to trim it even more. But I'm going to swap this out for a circuit that's already been trimmed. I'll show you that code. Can everybody get all of the LEDs to go on, like if you turn it the one way, and all of the LEDs to go off if you turn it the other way? Yep. Okay. Sweet. That's all I needed to know. I'm going to go ahead and swap this circuit out real quick. Thank goodness for prototypes, huh? So I'm going to go ahead and plug this in. So you can see here that all these LEDs are actually turning on. They're spaced out a little bit so you can kind of see them a little bit more clearly. Anybody else want to hold up their circuit and show it off? Sweet. All right, Amelia, it looks good. Anybody else? Hey, Moochin, there we go.
Trimmed by 300 actually.
Okay, yeah, you might have to trim it by a little bit more. Jackie's looks good too. Yeah, Dan, nice. Dan's got a beefy breadboard up there.
Wait,
I
I'm
think
sorry,
Amelia, you also had your large one.
what was the problem that was going on?
On my other circuit, I'll go ahead and bring it back here. You may have to pin my video, by the way. Sorry, I realize I'm still sharing my screen. I just wanted to share so you guys can see. So in this value right here, this ADC max, this is the theoretical max that the converter will output.
Okay.
Sometimes you have to trim it. So let me trim this by like 200 instead of 100. This might actually get me a better value here. And then so whenever you trim that value, sometimes it's going to bring you, there we go. So that worked. All my LEDs are turning on now.
I think it might have just been, I mean, maybe I'm wrong about this, but I think it might have just been like an error with like the logic in the for loop.
In the for loop?
Yeah, because if you do LED, like if LED is greater than I-1, then you can get, like without modifying the map inputs.
Yeah, so that kind of bypasses the logic. Essentially what you're doing is you're taking it down by, essentially what I'm doing here. You're taking off a fifth because you have 5 LEDs. So if you do I-1, it'll do that. This actually is the accurate code for it, but that's another solution for this problem.
Yeah.
So you're not wrong. It's just a different approach. Typical of coding. There is a wrong way sometimes, but most often there is another solution to what you're doing. But yeah, so that would solve the problem, but it may break some aspects of the functionality if you were to add more LEDs.
Yeah.
Does that make sense to everybody? Sweet. So yeah, fun little toy to play around with, I suppose. As far as usefulness, there are tons of things that you can do with this. I actually have, I don't know if I have a good way to show you guys, but I have this circuit right here, that this red component that you see that I'm pointing to, see if the camera decides to focus on it. Force focus, there we go. So this component is actually a bunch of LEDs lined up in one convenient package. Stuff like this was used on old, what are they called? Like amplifier boxes and stuff. You set up a home stereo. You used to have a different amplifier box that would connect to your TV, connect to your CD player, connect to your, oh my gosh, cassette tape player. I don't know. It's something that you connect it to that's old fashioned. And these used to be able to display like levels. So say if I had, I don't know, a microphone, which I do around here somewhere, and I plugged it in, I would actually be able to get a decent representation of the volume of the sound going into the microphone by using something like this. So if you had more LEDs, say, you could have like a volume meter or something like that. Let me actually see if you guys have a couple of minutes. I don't want to make this workshop run nearly as long as the last one. Let me see if I can grab a microphone and plug it in, see if we can get it to work. I actually just got these today in the mail. I meant to get them earlier, but Amazon was a little bit slow, as I've already talked to Avery about. But yeah, I meant to have these in the workshop tonight because I thought it'd be, you know, a cool practical application for what we're doing, but apparently not. So let's go ahead. I'm just going to see if I can replace this one for one. No idea if it's going to work. Actually, I might have to move some stuff around. Looks like ground has to be on the far left. Let's go ahead and try that. So ground is on the far left. No. Ground is in the middle. Damn it. Okay. Out is on the far left, and then VCC is on the right. Hey, there we go. Got some serious lights. All right, it's actually outputting a decent amount. It's funny, actually, the best way to see this is actually that little LED on the side. Let me go ahead and turn off this light again. So you might notice that whenever I speak, the LED turns on. So that is actually a great example of analog to digital conversion. That may actually just be a straight up analog circuit. But let's go into the serial monitor here, and maybe I can get this to trim a little bit. Okay. It's giving me all sorts of random values, which I think is funny. There we go. How's that? Oh, that's weird. So this is inverted, actually. Let me go ahead. I'm going to make some changes and see if I can get this circuit working for you guys. See, we do some cool stuff here. Just takes a while. So can you guys still see the LEDs on the side? Okay.
Yep.
So what I'm going to do is I'm actually going to invert this. So instead of 0 to ADC max minus 200, what I'm going to do is I'm just going to do ADC max minus 200, 0. And that's actually going to invert the mapping. I believe this is probably closer to 300. And the minimum value is probably closer to 20. That's just my guess. I'm going to change some values around and see if I can get this close. Oh, there we go. So it's not completely accurate, but you can see whenever I speak, it changes a little bit. I'm sorry, that's probably really loud for you guys. But yeah, so this is another just practical application of what you can use this kind of software for, what you can use this kind of hardware for. And yeah, if you guys ever want to experiment with some of this stuff on your own, just let me know. Send me a DM. I don't know if some of you guys have seen, there has been a new IEEE kind of Discord. So if you're interested in joining that, it's more of like a shenanigans chat like we've had in years past. So it's not really serious stuff in there, and you'll get a chance to talk with a lot of the exec one-on-one as well. But feel free to email me or send me a message if you ever want to kind of play around with some of this hardware. I don't mind signing it out as long as we can track you down to get it back eventually. So yeah, any questions before I bring it to a close and just kind of hang out for a little bit?